Hello, this is section 6.2, day 2, and today we'll be talking about volumes of solids with known cross sections. And these notes are going to be slightly different than what you have in your notes packets, but you'll still get the general idea of what the concept is. So what we're doing is, it's kind of weird, but we are, instead of stacking cylinders like we did in the last section, we were rotating things around an axis of rotation. This section, let me show you this. I pulled this off of Google Images. So what we're doing is we're letting, like this is the graph of y equals x squared. And we're taking the base length from the curve to the x-axis, or whatever is being determined, and that creates a semicircle. That's the shape we're using. And you can see how that distance, as it gets bigger, your semicircle gets bigger. And here it's squares, and you can see as that distance gets bigger, it makes the square bigger. These are triangles. Now the rectangles, I know it's kind of hard to see, but the rectangles always have the same height, but the base length is getting bigger. But that's the general idea of the shape we're creating, is the base is going to be on the plane region, and that distance, what we did in the last section, or the day 1 was the radius, that distance now will determine the base length for whatever shape that pops off of the page and creates a three-dimensional shape. That's the idea. And you can see as that distance gets bigger and bigger, the shape popping off the page is getting bigger and bigger. Okay. Now, what we're technically stacking, so in day 1, we were stacking cylinders, we called them discs. In this case, we're actually dealing with prisms. And if you remember anything about a prism, it was always the area of the base times the height. So a prism is a shape on the base, the bases are parallel to each other, and they're connected by rectangles. So if you find the area of the base and multiply it by the height, that will give you the volume of a prism. And these are just prisms stacked on top of each other that are popping off the page. So if you look, if you take the integral out of the picture, that a of x represents the area of the base times dx. Well, dx is the width of each prism. And we're going to be adding infinitely many prisms together to give us the area of this three-dimensional shape that's popping off of the page. All right, so hopefully that makes a little bit of sense. And in the class, I have some really good examples that students have done in the past. We did this project, and hopefully we'll have time to do this project this year, but that's something so I can show you guys visually what it looks like. Okay. All right, so the idea is you've got to figure out what that base length is. So basically we're taking this x equals y squared. So I graphed it over here for you so you can see that this is just the square root of x plus or minus technically. And the distance, that distance from the top to bottom, like when we did the area between the two regions, top minus bottom, you can see you end up with 2 square root of x. That's this distance here. That's the base length. So that's always the first thing you need to find when you're doing these problems, is get the base length. The next step is to get the area formula you're dealing with. In this case, it's squares. You have squares popping off the page. And depending on where you are along the x-axis is going to affect that base length. Okay, so from here, now we've established our area formula. So now we're going to do 2 times the square root of x squared, and that's your area formula, because that's the area of a square, s squared. So that's the area formula for the base, depending on where you are along the x-axis. So you can see it gets bigger as the x values get bigger. But then you're ready to set up your formula. So you do the integral from 0 to 9. It told us that. We stop at 9. Of your area formula, 4x dx. And that's it. That gives you the volume of all of these different prisms being stacked on top of each other, where they start off small and get bigger and bigger. Right. Now, we continue with that 2 square root of x. We're going to keep with the same function and base length. We're just going to change the area, the shape that's popping off the page. So now we're dealing with a rectangle. So the area is base times height. And for the rectangle, they told us the height is 2. So notice I put that here for the height. And then the base length, again, is determined by 2 square root of x because it's the same graph. So we have the area of our rectangle, and then we're ready to plug that into our formula. So the integral from 0 to 9, that's the area for each rectangle. And there you go. All right, so a semicircle. Now in this case, you got to be a little more careful because for a semicircle, the area is 1/2 pi r squared. Well, the radius of the semicircle is half that distance. So we only want the square root of x to go in for r. We don't want the diameter. So we put the square root of x in there, clean it up. And then once you've got the area for one particular base, then you plug it into your formula, and that calculates all of those prisms stacked on top of each other. Okay. Here's an equilateral triangle. There's the formula. We'll derive this in class. Okay, but so there's the base length. That 2 square root of x is back because we want the full length that we'll plug in for b. Clean it up, and then you're ready to plug it in your formula. Now, a really common mistake is students will put pi in there. Are you revolving anything? Students will also feel the need to square the integrand. No, that's not part of the formula. It's just simply the area of the base times dx. That's it. So don't be careful. Watch yourself. You don't want to put pi, or you don't want to be squaring things you shouldn't be squaring. All right, here's a triangle with a height of 1/4, length of the base, and so forth. So, and then here's a trapezoid. Okay, so let's look into 2 other examples here. So it says a solid has its base a circular region in the xy plane bounded by, here's our circle here, with a greater than 0. Find the volume of the solid if every cross section by a plane perpendicular to the x-axis is a square. Now I need to go back here. All of these were perpendicular to the x-axis, so we did the integral with respect to x. If it's perpendicular to the y-axis, you'll need to do the integral with respect to y. Okay, and that's the same with when we were revolving. If you revolve around a horizontal, it needs to be in terms of x. If you revolve around a vertical, it needs to be in terms of y. Right. So looking at these 2 examples down here. So we have our circle graphed. And I tried to do my best to kind of show you what it looks like, but we're dealing with every cross section is a square. So that's my area formula right here. It's your square. So the base length, yeah, it looks like this is my base, is this entire distance. Well, the top part of the circle, that's the square root of a squared minus x squared. So I solved for y. Took the square root, subtracted x squared over, took the square root of both sides. You technically get a plus or a minus, but I think we're good to just do what we did earlier and just double that top distance. So that's what we're getting here. So that's the base length for each square. All right, and then I just cleaned it up a little bit. And then we're ready to plug it in. And then the volume is going to be this integral from negative a to a. That's, I'm going to go from negative a to a here, of our area formula dx. And then we use that symmetry trick. Since this is definitely symmetric, we can go 2 times the integral from 0 to a and write it that way. Okay. All right, and then here's another one. So same example 2 here. If every cross section is an isosceles triangle with base on the xy plane and the altitude equal to the length of the base. And again, we're still perpendicular to the x-axis. I think the notes, the more current notes, have a couple different examples in them. So it'll be good for you to go back and look through those. All right, so same idea. Start with figuring out this base length here, which we already did. That's the same base length. Then write the area formula for the shape we're dealing with. We're dealing with isosceles triangle. So 1/2 base times height. 1/2 the base is here. That's the base we figured out. and then it tells you that the altitude is equal to the length of the base. So that's why it's squared, the base squared. And that's where we're getting this answer. So then you're ready to set up your integral. And I use the symmetry again that we had figured out. 2 times the integral from 0 to a of our area formula, dx. And then you solve it. And your answer ends up being in terms of a. I didn't solve this one. Well, maybe I did. That this is? Yeah, never mind. I did. It looks like I carried down through here and solved it. And then this would be the answer for this part. So, okay, I know this is weird, but you have to practice these problems. The first step is, again, there's 3 steps involved. You have to get the base length. That's the first step. So top minus bottom. Or if you're perpendicular to the y-axis, it needs to be right minus left. So get the base length, then just establish the shape you're working with. In this case, a triangle. Get the formula for the area for a triangle, and then get it in terms of x. Plug in your base length and then height, whatever it's referring to. But get your area formula in terms of x. Then you're ready to plug that area formula into your integral. And don't do anything funky. Don't add pi, don't square things. This is not revolving around anything. So it's just simply the area formula and then dx. That's it. That is it. Because remember, you're technically finding the volume of a prism. Without the integral, it's just one prism. That's it. And now we're adding infinitely many prisms together to give us the volume of that interesting shape. Okay? So please do your homework. Once you practice these are not that hard. Much easier than the revolving stuff we did during part 1. So, but you do need to practice these because they are a little bit strange. So, okay, make sure you do your homework. Let me know if you have any questions.